Hello my dear students, this is Akash SD. Welcome to the ASD physics classes. Hope so you all are doing really great. So students, in this video we are going to learn about the permanent magnets, their types, the properties of magnet and the properties of magnetic field lines. Okay, so let's start the video with the topic permanent magnet. Let's see. A magnet is a material that generates a magnetic field without electricity and has a property to attract some specific materials like iron towards it. So the most important, permanent magnet means there will not be any electricity, but the material will have the magnetic property. Okay, so we can see very well this is not the electromagnet. Okay, now let's see. The magnetic field is invisible but is responsible for properties of a magnet, that we know very well, is it? Now let's see the types of magnet. First one, natural magnet. Let's see. These magnets are generally irregular in shape and weaker in a magnetic strength. Example, you can see lodestone, a form of magnetite Fe3O4 is the natural magnet. Directly we will get from the nature this kind of magnets. Okay, can you see here very well? Now we'll see after that the second kind of magnet, very important, that is the artificial magnet. Let's see what is this. So see here, these magnets can be manufactured in any desired shape and their magnetic strength can be adjusted to meet specific requirements. If we talk about the example, let's see here, they are made from materials like iron, steel, nickel or cobalt alloys. What are those? They are ferromagnetic materials and can be customized in specific shapes. What are the shapes are possible? You can see bar magnets are there, horseshoe magnets are there, or any kind of shape if we want we can make it. Which magnet? Artificial magnets, is it? Let's see. Now under the artificial magnet in our syllabus the bar magnet is there now, so let's go through the bar magnet. So we'll see one by one. Bar magnet, first one, a bar magnet is either cube or cuboid in shape. You know very well cube or cuboid, how it looks like, is it? Can you see it? Now other property we will see for the bar magnet. Second one, let's see. It consists of two equal pole strengths in magnitude designated as a north and a south pole. Remember that this M is the pole strength. We'll see later. So north means we'll write plus M and south will write minus M. What is small m? Pole strength. Okay, and you can see very well these poles are separated by a small distance called magnetic length of the magnet. Okay, next one, let's see. Magnetic length, also called which length? Effective length. So we can see magnetic length of magnet is less than its geometrical length. Because why? Because these poles are not exactly at the ends of magnet as shown. So here I am just going to draw here one magnet. Okay, I will just draw here the two-dimensional. So here you can see here, this is the bar magnet, just two-dimensional diagram we have drawn, is it? So remember that here the poles will be there, but they will not be exactly at the ends. They will be somewhat inside. So this is the north pole and this is which pole? South pole. Okay, so remember that here, if I write here this distance is called the magnetic length or the effective length. I will write here LE. Okay, and if we talk about here the geometrical length, so we can write here this length, actual length of the magnet. That is what here, that is the geometrical length. And remember the relation between them, empirical relation is there. We can write here effective length is 5/6 LG. Now this one here. Some other formula can be also there like LE equal to 9/10 LG, but this formula is the very popular. Remember that. Okay, now let's see further. As I told you, next one is what? This is the general properties of the magnet. So first property is the very important, you know, also directional property. Normally it is used in a compass and all that. So see here, when a magnet is suspended freely, it aligns along magnetic north-south direction of Earth in a magnetic meridian. Remember that magnetic meridian, not a geographic meridian, magnetic meridian. Second one, monopole non-existent. So see here, if a magnet is broken into number of pieces, then each piece behave as an individual magnet rather than isolated poles. What can I tell here? See, so let's take for example, here I have taken here one magnet. Okay, so you know very well here, no? So let's take this is the north pole and this is the south pole. So what is happening that let's take this magnet I have cut from here. So the moment you will cut the magnet, do you think the north and south pole will separate? No. What will happen that here, the moment you will cut the magnet, here again one south pole will generate and here again one north pole will generate. So after cutting one magnet, you will get the two magnets. In further videos, we will learn about the cutting of the magnets also. And remember that there is the one law is there, Gauss law of magnetism. According to Gauss law of magnetism, closed integral B dot ds is 0, and this one is also about the non-existence of magnetic monopoles. Remember that we will learn all these things, not a problem. Okay, so after that we are going to see the further. Let's see the next property. The property is here, loss of magnetic poles. So see here, unlike poles attract each other while like poles repel each other, similar to charges in electricity. Is it? So remember that here, if in case what is there, north pole is there, I will write here with the M, and here also let's take north pole is there, I have written with the M. So what will happen that here between them, what will happen? The repulsion will happen. Remember that this is plus M, this is plus M. What will happen here? Here repulsion will happen. Remember that here. Is it? First case. Okay, first case. If I talk about the further, let's take for example, if I write here the minus M and minus M. Which poles are there? You can see both are the south poles. Again, what will happen? Repulsion will happen. And next one, if I talk about the unlike poles, let's take for example, this is minus M and this is plus M. Here what will happen? Here attraction will happen. So remember that here in this first situation, what is happening? There is the repulsion. In second situation, what will happen? The repulsion. Here what will happen? Here it will happen attraction. Is it? What is small m? Small m is the pole strength. Okay, so remember that this thing. Fourth one, repulsion is a sure test of magnetism. How can we tell? See here, a pole of a magnet attracts the opposite pole, and most important, unmagnetized magnetic material also, while repel similar pole. So sure test of magnetism is repulsion but not attraction. What it is telling here? It is telling that if in case, for example here, no, this is the case number 3 was there, is it? So if I talk about the case number 4, what is happening that, let's take for example here, we can tell north pole is there. So what will happen that here, near to this north pole, what will happen that if near to this north pole you are taking the north pole, so what will happen that here in this situation repulsion will happen. Is it? Or even if I take another case also, let's take south pole is there, near to that you are taking south pole. So what will happen that here also what will happen? Repulsion will happen. But let's take for example, if I take here, let's take for example, north pole is there and near to that I have taken here unmagnetized material. Which one? Unmagnetized material, no? Not having any kind of magnetic related property. But here also what will happen that here attraction may happen. So you can see very well, even unmagnetized material can be attracted towards the north pole, or we can write this also depending upon the situation. Even this is the south pole and here let's take unmagnetized material is there now. So here also what is possibility? Here also attraction property is possible. Okay, so remember that what this point is telling. This point is telling that repulsion is a sure test of magnetism. When the repulsion is happening, then only we can tell the material is having the magnetic property. Okay, attraction, why not? Because attraction can happen between the unmagnetized material and the pole of the magnet also. Okay, remember that. Is it? Now we'll see the next one. Very important, you know also before this what is given. See, magnetic field lines in a short form MFLs. Here you can see one diagram is there, diagram of the bar magnet. So this is the north pole, this is the south pole. We know very well from the basic in case of magnetic field lines will start from the north pole and they will enter into the south pole. Is it? So outside the magnetic field lines where to where? North to south pole. But inside the magnet, what will happen that here? Inside the magnet, the field lines will be from where to where? South to north pole. Remember that. Is it? So that only we are going to see here. See, in order to visualize a magnetic field graphically, Michael Faraday introduced the concept of field lines. What are these concepts are there? Let's see the properties of MFLs. So you can see first one, MFLs are closed curves, always closed curves, never open. Second one, outside the magnet, MFLs travel from north to south pole, while inside the magnet, MFLs travel from, as I told you, south to north pole. Remember that here. Is it? After that, we'll see the further property also. Let's see here the third one. MFLs never intersect each other. Two or more MFLs will never intersect. Remember that. Fourth one, MFLs emerge or enter in the surface of a magnetic material at any angle. What do you mean by the any angle? So let's take for example here what is happening that it is coming out. So it does not mean that this angle is a 90 degree. This can be any angle. Okay. And here also when they are entering, they can enter at any angle. Okay. So this thing only they are telling. Next one, let's see. MFLs, that means magnetic field lines, exist inside every magnetic material. Sixth one, at any place, crowded magnetic field lines represent stronger field, while distant magnetic field lines represent weaker field. So by seeing the diagram, you can see very well where magnetic field is strong. You can see very well the field lines are very close near the north pole and south pole. That means their magnetic field lines are very, very strong where? Near the poles, maybe north pole or maybe south pole. Okay. Next one, let's see. Last property. Straight and equidistant magnetic field lines represent uniform magnetic field. So remember that here, if in case we are representing the magnetic field lines like this. So here you can see they are straight also and they are equidistant also. What is the meaning of the equidistant? Let's take for example, if the distance between these two lines are A. So here also distance between two lines is what here? A. So this represents which one? They represents here the uniform magnetic field. Remember that here. Okay. And this thing is only possible when we are seeing any region is there very far from the magnetic field. There only it will appear like field lines are very parallel to each other. Is it, students? So I hope so. This video is very, very clear to you. Keep studying, keep growing.